let's look at something like this. So I want to do an angle problem. I want to do a good angle problem. There's a really important point. Have you guys done angular physics stuff yet in your physics class? Like rotational? Yeah.
Yeah.
Okay. Okay, so one of the points I want to make is that when you are mixing linear variables with angular variables, do you guys get, and this is for not just physics people, this is for everybody. You guys will all do some of this in your college. You all take a little bit of physics. I mean, you'll all do a little bit of this, I guarantee. And in your calculus class, you'll see this probably too. How do you deal with the angle? Do you know? You have to use radians, right? You always have to use radians if you're mixing linear and angular variables together. It's a must. And there's a really simple way to defend that for yourself so you can remember it. A good way to remember that rule. Degrees are, we probably talked about this at some point, but degrees are completely arbitrary, right? I mean, degrees, why did we make 360 degrees? I mean, think about why did we make 360 degrees for one circle?
Because it's a number with lots of factors.
Yeah, it's just highly divisible, right? It's got lots of factors. So you can divide it into fourths and make quadrants. It's easy to divide up into convenient subsections, right? But we could have picked 3,600, we could have picked 100, we could have picked anything, right? We just happened to pick 360 because it just seems like a good number. So it can't have any intrinsic meaning because it's made up. So you really can't use it for anything when you're doing trig. You really can't use it for anything except when you're making comparisons with other angles, right? Anytime you're doing any kind of a computation that's more complex, where you're actually involving angles in a larger problem, which typically has some linear parts too, you can't really, I mean, you should never use degrees. It's one of the biggest, most common sources of making an error, like in a physics problem, is not converting to radians first, right? Radians mean something. Think what a radian actually means. We'll take just a second here. It's kind of early celebration of Pi Day, I guess. Or just a preview of Pi Day, things to come. So if you think what a circle, you know, where the radian measurement really comes from. Right? Radians are measurements of what? You can tell me. I mean, think back to your trig days.
The radian is a measurement of how many radiuses around the circle the angle is.
I mean, kind of, yeah, that's a way to think of it. But there's another way to conceptualize this that's, I think, is going to be tying more with what you've done in trig.
Ratio of R1 to radius.
Yeah, I mean, but once again, it's on the unit circle, because the unit circle is amazing. Unit circle, I love the unit circle. Unit circle will change your life. Right? Unit circle does everything. You can do almost everything you guys have done in trig can be represented pretty well in the unit circle in a way that's really compact and convenient, right? So think what the unit circle is. When you talk about, if you talk about something like this, like let's say we've got, here's our x-axis, here's our y-axis. If I pick a point up here that's at, for example, something we could call 30 degrees. Okay, what do you know about the point at 30 degrees? What can you tell me? Maybe x and y coordinates, right? So what are the coordinates of that point?
1/2 square root of 3 over 2. Other way around.
Other way around, yeah.
I did sine negative or something.
Okay. Something else you'd probably include there would be what?
Pi over 6.
Okay, the radian measure of that angle. Agreed? Okay. Pi over 6. If we went up to, like up to 60 degrees,
And you just take that one versus.
right? And then that's going to be pi over 3, right?
Yes.
Okay. That really doesn't stand for an angle, though. What it really stands for is an arc length along the unit circle. It stands for the distance subtended, the length of arc subtended by that angle, right? What's our definition of circumference?
2 pi r.
2 pi r, right? But the radius of the unit circle is,
2 pi.
what's the radius of the unit
Circle
circle?
radius.
1, because unit means 1, right? Unitary is, in math means 1. So if the whole circumference is 2 pi, you get that 30 degrees out of 360, what is that? That's just going to be 1/12. Is that right? Yeah, 1/12 of the entire angle, right? Well, think about the length of arc. If walking around this, if an ant walking all the way around this is walking 2 pi, then he's only walking 1/12 of 2 pi, which is, what do you know, pi 6. So it actually has an intrinsic meaning to it, right? It's the length of arc subtended in a journey around the unit circle, okay? If we were to make this a non-unit circle, well then, that's no big deal. All we have to do is multiply that distance by whatever the new radius is to find out what the length of arc is, right? But the angle stays the same. So the angle is the length of arc subtended on the unit circle, right? So one circumference is 2 times pi times 1, which is 2 pi, okay? That's never going to change. That's a property of all circles. So radians mean something, degrees do not, right? Okay. So we'll talk more on Python. So let's go back to this problem then. So we got some angular stuff going on. Let's orient ourselves. This is interesting. If you're thinking about mechanical engineering at all, this is the kind of stuff that you would potentially study. A good friend of mine in college was a fellow physics major. He ended up being a mechanical engineer, and he's running a big lab where they design high efficiency automobile engines, and he does really cool stuff. So he does a lot of stuff with this kind of thing where they're looking at how are they going to optimize the performance of an internal combustion engine, and there's a ton of factors that go into that, as you'd imagine, but he has a lot of fun. It's a pretty cool job. So this is essentially how a car works, right? In a car, let's just talk about what powers a car. So you've got these cylinders, and there is, in the cylinder, to drive the car, we just explode a mixture of gas and air, right? And so there are valves that open up, and it injects in some fuel, and it injects in some oxygen or some air, just air at the same time, and they mix in a way so they're going to mix well. It's like we want it to be kind of turbulent mixing, and there's a lot of physics going on. But they mix in the chamber, and then there's a spark plug that ignites the mixture. It explodes. It drives the piston, and then another valve opens, and the exhaust gases are pushed out, and they come out your tailpipe in your car. And that just repeats over and over and over again, right? So if it's a little car with a 4-cylinder engine, it's got 4 of these things working in tandem. If it's a big car with a V8, then it's got 8 of these things working in tandem, right? And this is the part that's really interesting. This is just all very mechanical, but it's cool how you can take something mechanical. You can take this intrinsically linear motion of the piston, right? You're driving the piston down the bore in this cylinder. It just slides down this way, and then it's going to get pushed back by the rotation of the car, right? And then we ignite it again, and it applies a large force and pushes the piston down the cylinder, right? And look what it does. It's going to drive what's called the camshaft. It is an ingenious little design. So it's going to push on this. This is the fixed point that never moves, right? This is the center of the axis of rotation. So this thing is just going to rotate around and around and around. But it's pushing on this little lever that's attached to the cylinder. So you can kind of see, if you play this movie forward, as the piston moves this way, it's going to drive that point right there around to the, it's going to drive that point right here around to the back of its rotation, isn't it? Right? And then as this thing turns back around, as it continues to turn in this direction, it's going to drive the piston back into its starting point. Okay? Now there's no calculus or physics, or there's physics. There's no really calculus involved in this question. But does that seem like that's not going to work very well, because you're going to push this thing in this direction, but then as soon as the gas is all burned up, this thing is going to start coasting to a stop, and it's going to be really jerky motion, right? So you're going to push it hard, and then it's going to coast back this way, and then you push it hard, and it's going to go real fast for a while, and then it's going to coast, right? Oh, yeah, you bet. Yep. Uh-huh. So there you go. Uh-huh. So how do we fix that?
Offset, you should have 4 cylinders
Okay, so you offset them, that's one thing you do, you offset them, so there's almost always one of them pushing, right? But even then, there's gonna be some parts where it's gonna, if you didn't do anything else, the car would be kind of jumpy when you were driving it. Okay, what causes it to be smooth? This is kind of, I guess, more for the physics people, I guess, that are in physics now, but some of you will remember this next year when you take it. There has to be some momentum that keeps that thing moving around. But it needs to be rotational momentum, right? So the shaft is attached to what's called a flywheel. It's like just like a big hula hoop literally it's like a wheel inside your car where the mass is concentrated far away from the axis. And once you get this thing moving, the angular momentum is going to keep that thing moving. It takes a little while to get up to speed. It takes longer because you have to put a lot of energy into it to start to drive the flywheel, right? But once you drive the flywheel just kind of pulls this thing around in circles, right? So it gives it a lot of rotational momentum or angular momentum, okay? Does that make sense?
Yeah.
Okay. All right, so there's the nuts and bolts. In short, that's how an internal combustion engine works. That's how your car works. So now let's look at some of the detailed parts of this, because this is where the calculus comes in. This is the kind of stuff that engineers would do, right? So we know that we have this 7-inch connecting rod that's fastened to this shorter arm, right, which is part of the camshaft. And so the crankshaft rotates counterclockwise, so it's going in this direction, right, at a constant rate of 200 revolutions per minute. So once we get that flywheel up to speed and the engine's moving and we got the cruise control on, let's say, the engine is turning at a constant rate, and we know that the crankshaft in the car, which is attached to the axle eventually, right, this is what's turning the wheels in the car, it's moving at 200 RPMs, okay? Later on, there might be some gears down there that are going to make that, you can shift gears and turn that into more speed at the tires or less speed at the tires, but that's up to you. That's how fast the engine's running though, okay? We want to find the velocity of the piston, right? So there's the piston when theta equals pi thirds. So we're going to define theta as this little angle right there. Everybody see that? So it's going to be the angle between the longitudinal axis of the cylinder. So if you shined a laser beam straight down that circular cylinder, there's that laser beam right there. And the angle of that little 3-inch arm that's attached to the 7-inch arm, right, that's driving this thing, okay? So that's theta. There should be some relationship between that angle and the linear speed of the piston. And we'd have to be able to have that well defined if we're going to do some big mechanical engineering stuff, right? We've got to be able to define that relationship. Because later on down the line, we'd be looking at things like, okay, what's going to be, if we look at the explosion of that gas in the cylinder, we want to know where is the energy released the most, right? Where do we get the most bang for our buck? And we want to align that with the part of this motion where we're going to have the biggest torque and we're going to get the most force acting, right? So there's a lot of moving parts here, no pun intended, going on in this that we got to consider when we're looking at the mechanical aspects of a cylinder being fired, okay? Okay, so now we got to do some calculus. So what are the variables then? So we know this is the 7-inch arm, that's a fixed number. This is the 3-inch arm, right? That's a fixed number. But X is the position, is the horizontal position, right, of the piston inside the cylinder. That's going to change, isn't it? As the piston moves back and forth, that dimension right there. That's going to vary, right? And the other thing that's going to vary is the angle. There's another variable right there. Everything else is fixed, okay? So what information are we given here then? Let's look at this as a related rate problem, because really what we're trying to do is we're trying to find the rate of change. What would velocity be here, by the way? If we defined our variables as x and theta, what's velocity going to be? Everybody's agree that's x dot? You want to know how fast is that distance changing? And that's what velocity is. It's the rate of change of position, right? So velocity is just going to be x dot. That's what we're looking for, right? So step one That's the question we're answering. What are the snapshot values then? If we're taking a picture of this mechanism at that moment, right there, okay, what stuff are we given? Well, I guess that's it, right? There's one thing we're given. We're given the value of theta. We want the snapshot to be when theta equals pi over 3. What else are we given? 3 and 7, but those are fixed, right? We don't, angular velocity, good. Everybody get that the 3 and the 7 are never going to change. We don't even have to really include those in our snapshot values because they're constants. But we want to get the instantaneous values of all the variables or the rates of the variables, right? So yeah, look, we're also given this part up here. We're told that the rate of rotation of this thing is 200 revolutions per minute. Okay, those are bad units though, aren't they, right? We want those to be, what do we need? Our revolutions aren't really a great unit for us for angle. What do we want them to be in? Radians. Okay, radians per whatever. I mean, whatever we're measuring our distance in. Okay. So we could always make a conversion there, but we'll just leave it in minutes. That's fine, right? So we know that theta dot equals 200 revolutions per minute. So we've got to, first thing we got to do is we got to change those units. So here's a good review of changers, right? So how are we going to go from, we got to go from revolutions to radians. Okay? How can we do that?
4 pi over 30.
Okay, but let's do this in the language of a changer, right? And like this is something we would have done a lot. You probably do this in physics a bunch. I would assume you guys do this in like your chemistry classes too.
Yes.
But if we know we want to replace revolutions, does it make sense that we want revolutions? The unit that we're trying to replace goes opposite its original place so we can cancel it. So we have revolutions down there and we're going to get radians up here. So 1 revolution is how many radians? 2 pi. Okay, good. We cancel revolutions. We got radians where we want them, which is on top. And then while we're at it, let's go ahead and go to seconds. So I'm probably making this, you're going to probably go, this right, yeah, we get this, just hurry up. But just make sure, everybody's, remind you how this all works. So if we want to replace minutes, 1 minute is 60 seconds. So now we replace the minutes and our units work out the way we want them to, right? We end up with radians per second, okay? So what do we get if we simplify all this? Let's see, we could,
20 pi over 3.
20 pi over 3, thank you, there we go. 20 pi over 3 radians per second. So there's our snapshot value for theta dot. Okay, we good?
Yep.
Okay, so there's step 1, snapshot values. We know what we're trying to find. What's step 2?
Use that law of cosines.
Okay, so I gave it to you, right? I
Yeah.
mean, it's just reminded, you probably are well familiar with that from pre-calculus, but we want to come up with the parent equation, right? So we want to, ignoring all the rates, we want to come up with a static equation, right, so with no rates in it yet, that relates, in this case, it looks like thetas and x's, right? Well, there's our guy, right? In our situation, let's see, what do we get? 7 is, our b is 7, right? And our a is 3, and our c is x for our situation, right? So the law of cosines as it applies to our situation here, so our parent equation, would be x squared equals 3 squared plus, oops, you got it backwards, don't I?
Yeah.
Yeah, I do, got it backwards. So we get 7 squared, that's fine. 7 squared equals x squared plus 3 squared minus 2 times a, so that's just going to be 2 times 3 is 6 x cosine theta. We good? Okay. You good with that? Is that right?
Doesn't the 3 squared come first? 3 squared plus x squared
Oh, you're right, those should be switched, yeah. But that mathematically won't make any difference. Did I get that right, though? I think I did. So B is isn't that right? B is 7, A is 3, C is X, A is C, yeah, I think it's right. 3 times, yeah, okay. Everybody just double check me on that.
Shouldn't the angle be in between the two?
It is, between A and C.
Between A and C,
Yeah, okay.
right? Because it's,
And I think that's correct.
and C, I think it's right. I think we're good. Okay? Okay, so there's our static parent equation. Now what? Okay, so now we gotta differentiate, right? Okay, so we end up with, if we differentiate this, so step 3 is we're gonna relate the rates, right? So this is where we differentiate. Differentiate implicitly with respect to t, right?
Would it be easier to use the law of sine?
Well, we could, maybe. Let's see, law of sines, so what would that give us? We get, do we know, well, we don't know any of these angles though,
Oh.
right? So we're stuck. And they don't give us, they don't give, I mean, we actually could calculate x though, couldn't we, if we wanted to? Everybody agree?
Yes.
I mean, x is, we could find that pretty easily because we know that the value of theta is pi thirds, and we know 3 and 7. So we could actually calculate x if we wanted to. If we need to, we can, right? We can always go back and fill in extra information in step 1 like we talked about yesterday, right? We can always add to that as necessary, okay? Okay, so let's just differentiate then. What are we gonna get? So if I differentiate each of these terms, I'm just differentiating both sides of the equation with respect to t. So what about, Katie, what am I gonna get here? If I differentiate this guy with respect to t, that's a 7, yeah. So that's just a number, isn't it? So I'm gonna get, if I differentiate a constant, I get 0, good. So I'm getting 0 on that side. The derivative of x squared with respect to t is what? What am I- 2x is that derivative of hand squared. Very good. So I'm gonna get the derivative of hand squared is 2 times hand times the derivative of hand. There's my x dot, right, which is what we're looking for, okay? Plus 0, so we can maybe just ignore that one, right? So then I'm gonna get my minus 6, and then how about if we just do all this stuff? We got a product there, don't we? Right, we product the thing we gotta do, okay? So I gotta take the derivative of x times cosine theta with respect to t. We gotta be careful with this thing. So let's go ahead and treat this as a u and that as a v. So what's uv prime?
Negative x sine theta dot.
Okay, does everybody see that?
Yeah.
Because I've got x times the derivative of cosine theta. Derivative of cosine theta is negative sine theta, but then the derivative of theta with respect to t is my theta dot, okay? Plus v times du. Cosine theta x dot. Okay, good. And then all I've got to do now is just isolate the x dot, right? Okay. So what's that amount to? So I've got to distribute, let's go ahead and clean this up. If I distribute my negative 6, 2x x dot plus 6x sine theta theta dot minus 6 cosine theta x dot. So here are my two x dots. So I could either push why don't I just push these to the other side, the x dot terms to the other side and leave that positive, okay? So there's my equal sign, so I'm gonna leave this guy over here. And I'm push that to the other side, so I'm gonna get a positive 6 cosine theta x dot minus 2x x dot, right? Factor out an x dot. This should look pretty familiar from last section, right? Factor out an x dot and divide by what's left, and what do I end up getting for my answer?
6x sine theta dots divided by
6 cosine theta minus 6x.
Right? So if I factor these guys out front, I'm just left with a 6 cosine theta minus 2x, which I'll divide to the other side. Okay? And so step 4 is just plug and chug, right? Plug in values. So what do we know here? We know theta, we know theta dot, but we don't know x. So we do have to go back and solve for x, don't we? Right? Where's a convenient place for us to go back and solve for x? I mean, none of it's super convenient, honestly, but where is the step? We've already done some of the work here. Where would I go to solve for x?
go back to your
Yeah, right there, right? Everybody agree? If I go back to the parent equation, okay, but we do have the benefit here. That looks pretty ugly. It looks like I've got x's and thetas, but we know theta, right? So we can just turn that into a number, right? Okay, so theta was pi thirds, okay? So if theta is pi thirds, what's cosine of pi thirds? So that's going to be unit circle.
1/2.
That's convenient, isn't it? That's right up there, right? So the cosine's the x coordinate. So there's cosine. So we can replace that with a 1/2. So what do we end up getting? 49 equals x squared plus 9 minus 6 times 1/2, so minus 3x. Well, that's looking not terrible. That's just a quadratic equation, right? If we put that in standard form, I could subtract the 49 to this side and combine like terms, and I get x squared minus 3x minus 40 equals 0, okay? And that actually factors, doesn't it? Ah, what do you know, right? So we can factor that into x minus 8, x plus 5 equals 0. And so what are my solutions? Okay, let's go back to the problem. Do both of those make physical sense? So x is this measurement. X is this measurement right here, isn't it? Right, that's x. Could x ever be negative? Doesn't make sense for it to be negative here, does it? The distance between the center of the drive shaft and the head of the axle, right, or the piston, always has to be positive. So we could just abandon that one. And so what do we end up getting? X equals 8, so we can add another term. If we go back, we can add another piece to our snapshot values. X equals 8, measured in inches, right? We're measuring in inches, okay? And so now we've got all the pieces we need to get an answer, right? Okay. So what is that going to give us? We're going to get, if we plug all that stuff in, x dot is 6 times x, we said was 8, right? Times sine theta, that's going to be square root of 3 over 2, sine of pi thirds. That's a theta dot. Theta dot we have. Theta dot is 20 pi over 3, right? divided by 6 cosine theta. We already said cosine theta is 1/2, so that's gonna give us a 3 minus 2 times 8. Well, somebody, real quick, what is that? Let's take a decimal. What is it again? That what you got? Well, it can't be, no, we have a square root in there, it's gotta be. I mean, it's gonna be some weird decimal. See, maybe it rounds to 3.5. But, you know, we're gonna get some number, right? That's how fast it's moving. Okay, that making sense? Okay. Yep. Yep. That page?
Negative 66,
That sounds about right.
or negative 66.9710.
Okay, so let me write that down real quick, and then I'll go
It
back.
actually does go out to, fraction.
So, well, it can't be, because I have a square root in there. Well, I mean, there's no way. It can't.
My calculator's weird.
I mean, it might round to something that looks like a fraction, but I'm 100%, it absolutely can't, because that's an irrational number and that's an irrational number, right? So it can't be, but, so it works to have to be negative, what is it again, 66 point?
97.10.
So 67.0 inches per second, okay? And I would, anytime you're doing physics, you always want to go back and say, does that make sense? Yeah, that makes sense. That seems reasonable, right? That piston's going pretty fast. 67 inches, what is that? That's over 5 feet, 5.5 feet. So it's moving about 5.5 feet per second. It moves fast, right? In order to drive that shaft around. Why is it negative? Well, because X is getting smaller, isn't it? Even that part, you want to check the sign of this thing. If this thing is rotating counterclockwise, then, you know, when that's pi thirds, clearly it's got to be getting, right? It's turning in this direction, so isn't that going to make X shorter as this thing travels around? Right, so X is getting smaller, hence the negative rate of change of distance, right? I think that's a pretty cool problem. I mean, you can do, you know, we can actually do that now. We can actually do an analysis of what's going on inside a pretty complicated situation.
And
You should feel pretty good about that. You take all that trig, you know, you added some calculus to it, we got a little algebra going on there. You actually can do stuff now. You're pretty good at math if you can do something like that. Yeah.
if we were spinning in the opposite direction, would we still get the same answer, it'd just be positive?
It'd be positive, yep. 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 Yeah, and you know that because it's a reversible system. If you reverse the arrow of time, right? Yep. 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 Question? Oh, what page?
How do you get the extra minus
Right here?
Yeah.
So all I did was I just subtracted 49 from both sides. 9 minus 49 is negative 40. Right, all I did here was I just pushed that to the other side. To put it in standard form, set it equal to 0, right? Okay? Questions? Go. For whatever time you have.